Welcome back to our series on electricity and magnetism. In this particular episode, we're going to continue talking about capacitance. Here, we're going to look at the energy contents of a capacitor, and then further, we're going to look at a dielectric and see what happens when we insert a non-conducting material in between the plates of a capacitor. Okay, first, let's re-examine our parallel plate capacitor and talk about what happens while it's charging. So if this is the positive and negative terminal of some sort of external source of voltage, then of course we know that the capacitor is going to slowly charge up, gathering positive charges on one plate and a corresponding amount of negative charges on the other, because all we're going to do is pump charge from one plate to the other. Well, while that happens, work is being done. It doesn't take any energy to, say, move the very first charge, but every subsequent charge, there's going to be a voltage gradient that in essence the charge has to climb in moving from one to the other. So let's look at the work that's done. Well, the work that's done is really a change in energy, and we know that energy is related to the voltage times the amount of charge that's changing. So for each little piece of dq that we move, say, from the negative plate to the positive plate, the voltage that it experiences times that charge will give us the amount of work that's done. And of course it's done incrementally, which is why I've expressed it here in terms of differentials. Well, let's go ahead and make a replacement. We know that the capacitance of any capacitor is equal to the ratio of the charge it contains divided by the voltage. So let's replace the voltage with Q over C. Now, I've changed the variable from large Q to small q because it's still a little bit of charge. We're adding on the charge incrementally, and of course dq is still there. So if we look to integrate both sides here, that's going to give me the amount of work that's done. And of course that'll be the integral from the initial charge to the final charge. We'll just say 0 to big Q. In other words, we want to charge it fully, add on the full amount of charge it can hold. And that'll be Q over C dq. Well, that's going to equal 1/2 of Q squared over C. In other words, that's the work it takes to charge the capacitor from 0 all the way up to a full charge of Q. And of course, all this work then is going to be stored in the potential energy of the position of those charges within the capacitor. In other words, it'll be stored in the electric field. So we can think of this as a kind of potential energy. This is the potential energy in the capacitor. It's really energy stored in the electric field between the plates of the capacitor. And one way to express it is 1/2 of Q squared over C. But of course, capacitance is related to Q and V, which means if I wanted to, I could replace the C down here with Q over V, and that would also make 1/2 of QV. That's another form of the potential energy of a capacitor. And of course, because Q is equal to CV, a third way to express it would be 1/2 CV squared. Now, all three of these are interchangeable, and we look at the units they produce, they all produce units of joules. So this will truly be an energy, the energy stored in the electric field in between the plates of a capacitor. And this would work for any shaped capacitor. So this energy function works regardless of the size or shape of the capacitor. You just need to know its capacitance. In addition, you need to know the voltage or the total charge on it. As long as you have two of those three pieces of information, you can calculate the energy stored in that capacitor at that time. Well, our next stage is going to be to talk about what happens when the space between the capacitor is filled with some other material besides air. Imagine that we took this capacitor and instead I'm going to fill the space in between it completely with some sort of dielectric. It would have to be a dielectric because if I filled it with some conductor, of course the conductor would just join the two plates together and I would get a flow of current through it, but I wouldn't be able to store current on the plates any longer. Well, it turns out that every material, every dielectric has associated with it a dielectric constant. We will use the Greek letter kappa for our dielectric constant. And kappa is a dimensionless quantity. It's simply a multiplier. What it does is it multiplies the capacitance the capacitor would have had with air or empty space in it by the kappa value, which basically increases the capacitance. Kappa is always greater than 1. And the reason why is empty space has a kappa value or a dielectric constant of exactly 1. Air is slightly higher than that, and all other dielectric materials are higher than that still. What in essence happens here is inside the dielectric, while it can't carry a current, it's not a conductor, it can slightly polarize, and that polarization will correspondingly reduce the amount of electric field in between the capacitor plates. That correspondingly reduces the voltage, and a decrease in voltage will produce a corresponding increase in capacitance. So the formula for the new capacitance with the dielectric present is kappa times the original capacitance. The capacitance assuming that the space in between the plates was empty. So you can always calculate the new capacitance of any capacitor with a dielectric inserted. Dielectrics really serve two purposes. One is that they can mechanically strengthen the capacitor by providing, in essence, a scaffolding to keep the two plates from moving closer to or further apart. And the second thing, of course, is just by the choice of a good dielectric, we can dramatically increase the capacitance of the capacitor. Some dielectrics have capacitances of 2, 3, 4, even hundreds, and inserting them will dramatically increase the capacitance. They'll increase the amount of charge that can be stored per electric field. Well, because kappa is inserted in this particular formula, we can look at its impact on other formulas as well. We know that as the capacitance increases, correspondingly the voltage decreases, and of course the electric field goes as the voltage too. Imagine the electric field in between these plates. It's basically the electric field from a flat plane. And you recall that the electric field calculated from a flat plane was sigma over 2 times E naught. That is, that's the electric field in between the plates of a capacitor. All we had to do was remove the 2 to take into account the fact that each plate provided an equal amount of electric field. So this would actually be the electric field for a single plate. Well, in order to take kappa into account, we know that while the capacitance increases with the addition of a dielectric, the voltage decreases, and of course the electric field strength goes as the voltage. So this would be sort of E naught, which is, this is the electric field had we not had any electric field in place. And of course, you can see where we'll have to insert it. In order to find E, the electric field with the dielectric, it'll be sigma divided by 2 kappa E naught. You'll notice that kappa always hangs around E naught, and there's another interpretation for how we can take kappa into account in all of these electrical problems, and that is, all inserting the dielectric does is it changes the permittivity of free space in the space between the plates of the capacitor. That is, instead of thinking of it as impacting capacitance and impacting voltage and electric field separately, you can just consider it this way, that the permittivity is equal to kappa times the permittivity of free space. That is, we've been using E naught this whole time without really recognizing, well, why is there that naught on E naught? And the reason why is it's the permittivity of empty space. It's the permittivity of air. But if instead we put a dielectric in that space, it's going to impact everything E is used to calculate with, such that E will replace E naught's role, E being equal to E naught times the dielectric constant. And that includes our old friend Gauss's law. We know that Gauss's law is the closed loop integral of E dot dA. That is, we find the flux through a surface due to the electric field. And we know that that flux will be entirely equal to the enclosed charge divided by E naught. Well, now you can see how we can rewrite Gauss's law in the presence of a dielectric. It'll still be the closed loop integral of E dot dA, and it will still be equal to the enclosed charge over, but now it'll be equal to E, that is kappa times E naught. So if you do any Gauss's law problem where the space in between the plates where you're interested in drawing your Gaussian surface is occupied by a dielectric, you can simply alter Gauss's law by inserting kappa in front of E naught and basically recalculating E naught to be the new permittivity of not free space, but the permittivity with that dielectric in place. Well, that's about it for capacitance. We've looked at its definition, how you can calculate capacitance for different geometries of capacitor. We have looked at the capacitance of series and parallel capacitors, which will be very useful when we start looking at circuits. And now we've looked at the energy stored in a capacitor and the idea that a capacitor can interact with a dielectric and what are the implications of that happening. Well, now we're ready to move on to current, resistance, voltage, and electric circuits.